Okay. Hello, dear audience. I am Jisoo, and these are my lovely teammates. Our project is recognizing the precipitation from the CCTV video. Rainfall. It is a very important meteorological data. High-resolution rainfall, high-resolution data can enhance the numerical weather forecasting model. It can tell you to bring your umbrella on rainy days or to evacuate when flood is coming. Typically, precipitation data are collected by automated weather station, but the device is expensive and we have only so many of them. In Kwack district, for example, we have only 2 stations. But how about CCTV camera? We have myriads of them. If we can infer the rainfall depth from these videos, we have access to enormous amount of data. There have been previous studies which applies video classification model for this purpose, but their limitation is that dataset is small and labels might be spurious because of the physical distance between the camera and the measurement device. Also, the number of their labels are small as well. In our project, we aim to overcome this by using the camera located right next to the AWS device, minimizing the error in ground truth label. Also, we have much larger dataset. We have several months amounts of videos, and we developed algorithm to automatically generate dataset from this raw data. And we choose 5 labels, which is more compared to 3 in previous studies. We choose S3D model, the newest one, in 2-stream approach. Because of the nature of rainfall video, we expect that teaching the model with optical flow will have great advantage. Also, S3D is computationally efficient than standard 3D convolution model. This is the architecture of S3D model, as you all might remember. We pass the frame into a spatial stream and optical flow to temporal stream. So, here's how we pre-process the datasets. There is no available dataset, so we had to start from scratch. We used 5-minute video to train the model, thus generated 5-minute rainfall labels from AWS data. Since the device measures the rainfall in discrete fashion, we averaged it to continuous rainfall and then accumulated to get 5 minutes rainfall. To reduce the data size, we perform temporal sampling on 5-minute video. To capture the frames evenly from total video, we first segment the frames and sample frames from each segment. To perform optical flow, we sampled consecutive frames from each segment, and we saved same number of RGB frames and optical flow frames, which will be explained later. On each frame from temporal sample, we performed spatial sampling. This is to reduce the data size and to make raindrops relatively bigger in the image. We defined 3 types of spatial sampling. The difference between them is how much the raindrops were magnified at cost of losing the data from uncropped regions. Now here are our results. First, there were various optical flow candidates, so we tried a quick test first. After our testing, TVL1 and warped optical flow showed good performance, so we used these 2 in our study. Because of the limited computational resources, we cannot pass all frames from spatial temporal sampling, which was very depressing. We had to use only a few numbers of consecutive frames to increase the batch size, and the best case shows 64% accuracy. This is the average performance for each method. One thing that's worth noting is that spatial sampling with minimal ROI loss showed the best result. And we probably introduced our best model. Okay. Now, conclusion. We trained S3D model with rainfall video and precipitation. Although we were handicapped by machine performance, the model shows decent accuracy. Thanks for listening, and thank you, our indicator, for your excellent lecture this semester.
Okay, any question? Yes, Angon?
Oh, thank you for the presentation. It was really interesting. And I just wanted to know that is there any baseline result that you can compare, since you only reported your results. So it would be better if there is some like baseline that can compare.
Oh yeah, let me share it again. The baseline were, well, we were we wanted to like acquire these comparable accuracy compared to the previous studies, but unfortunately our model was 60. It showed, where is it, 64% accuracy. Now it is not horrible. I think we can say this is kind of comparable. Also taking account that we have more labels for 3 to 5, and we have limited computational resources, but we're quite happy with this result.
But
Can I add some more details for it?
sorry, Hwisong, can you say that again?
Can I add some more details for it? Can you show the baseline? Yes. For here, they label for TSM model, they label 0.123 only, and for CNN is 0.2, 0.5, and 1. And the it's too big, and we are only have 0.1 labeling from 0.1 to 0.5. So if we do the same label accuracy with that, I think we can have more greater accuracy. Actually, for the TSN model, they do when they do 0.1, 0.3, 0.5, they get 90% accuracy. So I think if we change our evaluate data, it can be more higher.
So actually, yeah, I think these are not directly comparable because they use all different data sets. So it will be important to actually have the common data set and evaluation setting to compare these algorithms. And if this, yeah, I think it's comparable at least. So we probably need to do some additional experiments to actually compare on the same data set to actually have the conclusion. But thanks.
Thank you. Any more questions?
We don't have time. So
Okay.
yeah, if you have any questions, by the way, feel free to contact the presenter or the authors directly.